Brain plasticity, also known as neuroplasticity, is a term that refers to the brain's ability to change and adapt as a result of experience. Up until the 1960s, researchers believed that changes in the brain could only take place during infancy and childhood. By early adulthood, it was believed that the brain's physical structure was permanent. Modern research has demonstrated that the brain continues to create new neural pathways and alter existing ones in order to adapt to new experiences, learn new information, and create new memories. The brain possesses the remarkable capacity to reorganize pathways, create new connections, and in some cases even create new neurons. Brain plasticity can occur as a result of learning, experience, and memory formation, or as a result of damage to the brain. Dendritic branches change, i.e. elongate or retract, within a month of experience. Practicing brain games doesn't appear to help improve cognitive functioning, but exercise does, and it also changes brain structure. Perhaps now is a good point to address this question. Can new neurons be created? People used to believe that we're born with all the neurons that we'll ever have. More recently, researchers have identified some areas in the brain that produce new neurons. The olfactory bulb is unusual. It's the only place in the body where neurons are exposed to the elements. These olfactory receptors cannot last long in such a harsh environment, requiring renewal within 6 to 10 weeks of exposure. As one neurobiology researcher tells his students, by the end of the semester, you'll have replaced all of your olfactory sensory neurons. Oh, and that's about 40 million neurons. These new neurons are produced by nearby stem cells that differentiate and migrate to the olfactory bulb. The other part of the brain that appears to show neurogenesis is the hippocampus, an important structure for memory formation. Levels of adult hippocampal neurogenesis are reduced by stress and increased by interventions that are associated with beneficial effects on cognition and mood, such as learning, environmental enrichment, and exercise. If our brains are so plastic, what is the constant interfacing with technology doing to them? Our brains have evolved over millennia, set up to interface with the richness of nature. If experience shapes our physical brains, what effect does the modern world have on our physical brain? Are we, in the words of Nicholas Carr, welcoming the frenziedness into our souls? Although our brain is fed sensory input from multiple different pathways, we tend to experience events holistically. Binding, or large-scale integration, is the tying together of separate sensory inputs to a single cohesive experience. It used to be thought that binding occurred in the association areas of the brain, areas where no other identifiable functions occurred. But this is no longer believed to be the case. However, researchers still have no clear answer to the question of where, specifically, multisensory integration occurs. An interesting example of unusual perceptual binding is the fake arm scenario. In this setup, the participant can see the hand of a rubber arm in front of him, while the researcher simultaneously strokes his real hand, which is hidden from view by a barrier. For most people, within a short period of time, the tactile sensation and the visual input bind together, generating a compelling illusion. The fake hand begins to feel like the participant's real hand. The participant knows it's not his hand, but as he looks down at it, it feels as if it's his hand being touched. This is a hard experience to describe, so try it out for yourself. If you do, it's critical to touch the same point on the real and fake hand and to do it at exactly the same time, or the illusion will not work. Just as the fake arm illusion demonstrates how incoming sensory information can be misperceived by the brain. Phantom limb demonstrates how the brain can generate inaccurate perceptions when it lacks normal sensory input. The majority of people who lose a limb will experience the unusual and generally somewhat distressing perception that their limb is still there. Close your eyes for a moment. You don't have to look down at your arm to know where it is. You feel it there, at your side or extended out in front of you. People with phantom limb retain this same sensation even when their limb is physically no longer there. They won't look down and see a missing arm. They'll often feel that it's there. What's worse, sometimes people will experience pain in the phantom limb, perhaps the sensation that their fingers are bent backward or that their hand is continuously clenched in a tight fist. There's nothing they can change physically, so it's hard to treat such sensations. People used to think that these phantom limb sensations were generated from receptors in the remaining stump, so sometimes painful surgeries would be conducted to try and remove these sensory endings. People now understand that the perception of one's body is maintained within the brain. Indeed, the entire body can be mapped out to specific areas of the sensory cortex. Sensory input may modify this stored representation, but removal of a body part does not destroy the brain's perception of that body part. Imagine that someone stroked a blunt pencil gently across your cheek. You'd feel your cheek being stroked. But in a patient with phantom limb, that same action might also elicit a sensation of the phantom arm being stroked. The cheek and the arm may be represented in nearby areas of the brain's somatosensory cortex. Without input from the amputated arm, the area of the brain devoted to that part of the body is starved of input, and input from nearby body areas begin to encroach. So now, what should be devoted to the arm's input is now getting stimulated when the cheek is stroked. Phantom limb and phantom pain can be helped through further reorganization. One technique that has proved useful for many is the mirror box. By placing the good arm in the box and looking down at the reflected image, the brain visually interprets the input as the missing phantom limb. But this limb can now be visually modified by moving the intact arm, stretching out the fingers, circling the wrist. In much the same manner as the fake arm illusion, the brain begins to interpret the visual image of the reflected intact hand as his missing right hand, thereby modifying its representation in the somatosensory cortex. Brain plasticity in action.